Hello and welcome to All Math Considered. In this video, we want to see how one would go about finding the eigenvalues and the eigenspaces of a 2x2 matrix. So let us say we have a matrix A with entries 1, 10, 5, and -4. Our plan is as follows. First, I explain why we need to introduce a new variable lambda, and then consider the new matrix 1 minus lambda, 10, 5, -4 minus lambda. In the second step, we want to find those values of lambda for which the determinant of that matrix is equal to 0. Let us denote our solutions as lambda 1 and lambda 2. These are actually the eigenvalues. After that, we need to essentially repeat the same step for each of the eigenvalues. To start with, for the first eigenvalue, lambda 1, we need to find all the vectors x, y, which are the solutions to that equation here. 1 minus lambda 1, 10, 5, -4 minus lambda 1 times the vector xy is equal to 0. Another way to say this is that we are computing the null space of this matrix here. Finally, in the last step, we need to do exactly the same thing with lambda 2 taking the place of lambda 1. When looking for eigenvalues and eigenvectors of a matrix, we are actually searching for vectors v which are scaled by the corresponding linear transformation. To do this, we need to consider the equation AV equals lambda v, where lambda is the scaling factor, and then look for the solutions to that equation. We can rewrite this equation. First, by replacing lambda with a diagonal matrix with lambda on the main diagonal, and then as A minus that lambda diagonal matrix times v equal to 0. Of course, we have A minus the lambda diagonal matrix equal to the 2x2 matrix 1 minus lambda, 10, 5, -4 minus lambda. And this is the matrix we need to consider next. Specifically, we want to find those values of lambda for which the determinant of this matrix is equal to 0. This is because an earlier linear algebra fact tells us that such a non-zero solution V exists if and only if the determinant of the involved matrix is 0. Let us compute this determinant. We have 1 minus lambda times -4 minus lambda minus 50 equal 2 lambda square plus 3 lambda minus 4 minus 50 equals 2 lambda square plus 3 lambda minus 54. And then, using any method to solve this quadratic equation, we see that this equals to lambda plus 9 times lambda minus 6. We therefore find two solutions, -9 and 6, and these are precisely the eigenvalues of the matrix A. Let us now proceed with finding the eigenvectors for the first eigenvalue, which we have determined to be -9. This is the same as to find all the vectors x, y, satisfying the equation, the matrix 1, 10, 5, -4 times x, y equals to -9 times xy. Moving the right-hand side over to the left-hand side has the effect of subtracting -9, which is of course the same as adding 9 to the main diagonal of the matrix. So we get a new equation, the matrix 10, 10, 5, 5 times xy equals to 0. Solving this is simple, as already the first row of the matrix gives us the answer. We see that the solutions form a line spanned by the vector -1, 1. This line is also called the eigenspace, corresponding to the eigenvalue -9. It consists of the origin together with all the eigenvectors for that eigenvalue. We denote this line as E subscript -9. We now do the same thing for the second eigenvalue, lambda 2, which we have previously computed to be equal to 6. This time, we need to subtract 6 from the main diagonal of our original matrix. And we end up with the matrix equation -5, 10, 5, -10 times xy equals to 0. Solving this gives us the line spanned by the vector 2, 1. This is the eigenspace corresponding to the eigenvalue 6, and we call it E subscript 6. So our final answer is that our matrix has two eigenvalues, -9 and 6, and the corresponding eigenspaces are the lines spanned by the vectors -1, 1, and 2, 1. One way to think of this is that we now understand much better what the linear transformation associated to our matrix does to the plane. It stretches the vectors along the line 2, 1 by the factor of 6. It flips the line -1, 1, while at the same time stretching the vectors along that line by the factor of 9. And transforms all other vectors in the linear fashion, which is uniquely determined by what it does to these two lines. And so, this is the end of our solution.